Okay, thanks. Now, thanks very much, Sean. So I suppose there was a clicker there somewhere. I thought, but just a mouse. So essentially, a number of things I'm going to go through here in terms of the nuts and bolts of the project. But first off, what do you tend to need for a farm biogas plant? And as Sean has been describing, we're looking at a biogas plant where it's not going to interfere with the current farm production. We're not looking at displacing animals off the farm. We're going to take be it a dairy farm or a livestock farm, take the waste materials, utilise that in a biogas plant, and basically the biogas plant is a tool on the farm to enhance its current production and to lower its impact. So first off, there's two things really a biogas plant is that you're looking at. It's feedstocks and the energy use, and those two need to match out to make it a viable project. So first and foremost, in terms of feedstock, any farm, any matter from, so be it slurry, be it chicken litter, any matter like that from a farm, animal waste will work. But you need something with a good yield. So the first part is you need to get a good gas yield off it. That's what you're trying to produce. It needs to be as much as possible cheap and cost effective. So by cost effective I mean, or cost effective. So silage is quite a good substrate. It's expensive, but it produces an awful lot more gas. So therefore it brings in its own viability because of the fact that it produces more gas. You do need a regular supply, and as I go through the different examples we came across, this was a challenge and actually a blocking point for a number of farms, and that good quantities are available obviously to feed the biogas plant. So they tend to be the main things in the feedstock. You need good gas yield, cheap or cost effective, regular supply and good quantities. In terms of the energy use, in order to fund this project like this, in order to make it financially viable, you need to have a high value for the gas, so a high energy value use or revenue. So either you're selling the gas or selling electricity, selling an energy format, or you're displacing an on-site use of energy, which is a high cost on the business. So you need to be able to bring in the value through one of those. And again, in terms of that energy demand, if you're going to use that energy on site, the ideal thing is something that's relatively continuous and has been high cost. So, and I'll give an example of where the non-continuous requirement was a problem for some farms. And again, going back to the sale of energy with a high value. So in terms of 4 different types of farms we looked at, and just in generalised, so poultry, pig, we look at dairy and beef as well. So what we found with, say, poultry farms, and it's a good example of the feedstock has a high yield. There is a good gas yield off poultry litter. They tend to use different bedding materials. Some are using sawdust, some were using straw, chopped straw. Chopped straw actually would have had and pelletized straw in particular had a good gas yield off it. So it was a good yielding material. There was plentiful supply, large quantities produced in each batch. One issue was, or two issues was, number one, it couldn't be digested alone because the bacteria are just not able to. It's a dry, high nitrogen material. The bacteria don't like that, so you need something else to tone it down a bit in terms of the carbon nitrogen ratio. So slurries and other materials. So you need to have a co-digested product going in there as well. The other thing was disease control issues. So this became one of the bigger issues for poultry farms. And look, I would be quite familiar with other types of farms. I wasn't that familiar with poultry farms at the start of this, but the key thing on it was every poultry farm tends to work for disease control reasons. They do all in, all out. They might have 10 houses. They will fill all those houses on day one. They will raise all those chicks together at the very same age, and then when they get to maturity, they're all go out within a week together into the factory. And you're emptying out the entire farm, you're washing the entire farm down, all of the sheds together, and you're starting then with a new batch. So you've got a complete break between one batch of chicks and the next for disease control reasons. So that meant that the feedstock, the disease control side of it, storing large quantities of chicken litter on site was going to bring the disease risk from one crop into the next. So that was a considerable consideration. Most poultry farms, or practically all, they have contractors or people come in, take the chicken litter off site completely, and it's dealt with, ploughed into tillage or stored for use. So that disease control issue was a major point. In the energy use, poultry farms on paper look brilliant because they have a very high energy use. You put the chicks in, you want your houses at 25 degrees plus, from day one. You reduce the temperature over the first 25 days, where usually your heating is turned off by day 25. But so you have a wedge-shaped heat demand, energy demand, very, very high on day one. By day 25 it was gone. The chicks are gone usually by day 34, so it could be day 40, day 45, depending when the next crop comes in. So you had a big gap in the energy demand. A biogas plant likes to produce energy all the time, so it didn't suit, that intermittency of demand would not suit a biogas plant. So I suppose the main thing we found in the poultry farms was, obviously demand for chicken is regular, it's on a weekly basis or daily basis. So really and truly, poultry farms in a co-op structure would work very well, because you can balance off the supply of material, you can take the material off-site into a co-op structure for disease control reasons, and you would have then gas coming out, depending on what the use could be. It could be, if you want to go back to the poultry farms, you could, and that more than likely would be tankered, but you would have all different options then for the use of the gas, as we did find during the course of this project as well. Look, solid biomass actually provided energy a lot cheaper, and if you had a lot of gas, you'd be better off putting it to a higher value than say wood chip or something like that. So it was very good on paper. There is definitely potential for poultry farms, but more on a cooperative basis rather than individual plants. In terms of pig farms, the feedstock, generally loads of feedstock, plenty of it, but the gas yield was very low. Pig farms by their nature do a lot of washing, a lot of water washing on a continuous basis, and it's a very dilute substrate, so there was not a high amount of gas coming out of it. So you end up having to heat all this water in the digester, so that tends to lower it. It's still quite workable. We've seen, there's actually one of the original examples of an on-farm site was on a pig farm. It was planted operated for about 20 years here, and worked very successfully. And it was, but mainly was taking the feedstock from the finisher houses, which would be less dilute. The energy use on site would be quite good, and a regular demand on especially an integrated pig unit. In terms of dairy, the feedstock, a reasonable gas yield, plentiful supply generally on a dairy farm, but seasonal. So the seasonality was a big issue on most dairy farms. And the other side of it is, which was a big finding of the project, was having fresh slurry going into a digester is important. So the ideal scenario for a dairy farm going into a biogas plant is scraper systems, where you've got your slurry being produced, scraped into one tank, and then transported into an overground tank or lagoon, whatever, because you've got a point where you can capture fresh slurry every day or on a regular basis and take the gas from it. Slurry by its nature will lose a lot of its gas when it's in storage at the start, so you want to capture it early. And that was an issue. So where you see animals on slats or cubicles on slats, it was more of a difficulty to have fresh material. Your storage is, like your slurry is going straight down into your storage for where it's going to remain for months. In terms of energy use, limited to a certain extent, but dairy farms use a lot of electricity. So, and in particular, we've seen robotic milkers, you tend to have your demand over the course of the day rather than morning and evening milking. So the electricity use on farm definitely lended itself quite well in dairy farms. It gave high value to the biogas. There's also future potential for biomethane on dairy farms or for any system like that. In terms of beef, look, reasonable gas yield we did find. We looked at a small number of beef lots. The seasonal supply was an issue in some cases, but others were doing a feedlot system, so there was always supply in those. But again, that area of the slurry being stored in slats and getting access to fresh slurry was going to be a problem. One of the bigger problems on a beef farm was there was no energy use. You had no electricity. You could potentially look at biomethane for tractors in time, but as it stood, there was no real value for the electricity or for the energy use on site. So that caused difficulties in assessing them. So in terms of the evaluation tool, this is a condensed model to what we produced originally to assess all the different farms. This is more based on it's more of an economic and technical model here, but it's essentially the same model. So we will be putting a version of this up online very shortly, but ultimately, I'll just stand out a bit to be able to see it there myself. But trying to increase that size. But effectively what we're doing here, you can see all the boxes in red, they are for each farm the individual inputs. So you have the number of cows, the number of weeks housed, so that's a critical point in terms of dairy of your livestock, how many weeks you're housing for, and the different types of animals. Now we're taking the information in terms of kilograms of slurry produced directly from nitrates, regs and published figures. So you can put in all the different livestock numbers you have, the time housed, and we have in green is generally set numbers, like the amount of biogas you can expect to come from a cubic metre of slurry, but they can be changed by the person that's filling this out if they wish, but we have set values there. Other materials you can see down the bottom, such as grass silage, which is farmyard manure there, but other solid materials that could be brought in. Again, similar way you can detail up. That tool is basically so that the farmer can put in all the different materials they have when they've got them and assess to see that takes that into the assessment to see the potential gas yield. The second thing then is basically information in terms of the other parameters. So there's some increases here on my own screen. So first off would be the electricity demand on site, so how much electricity is used and at what cost per kilowatt hour. Other fuel use then, so in terms of heating, so this is a factor both on dairy farms for washing milking machines, and potentially you could look at a domestic house if it's nearby, or a couple of domestic houses. But you're looking at the different values. You can put in any sort of fuel you wish there and put in the various values that pertain to that, and it'll work out the heat demand on site. The energy sale values. So first of all, your own electricity, the electricity you're putting back out onto the grid. So are you getting a price for putting electricity back on the grid? And if you were selling heat, at what value you can do that. We also have the percentage there. So in this case, we're saying that any excess electricity, 100% of the excess electricity can be sold back onto the grid. But we put into this model. Sorry, go back there 1 second. We put in that model that there wasn't potential to sell the heat, so it would be wasted effectively from that. Other things there, such as your loan finance, so the rate, number of years you want to do it over, and if there's a capital grant available, at what rate and to what maximum amount. So you can add in those values as well. There's a number of technical parameters to do with the digester, so the efficiency of the CHP or generator, the excess size in the digester, which is an important factor, hydraulic retention time, maintenance costs. We put in 1.5% of the capital in this example. And if you're putting in labour costs as well, at this stage we should put in as zero in terms of the farmer will be doing it himself, and it comes out in the figure at the end. So there's two results page then coming out of it. One is based on the technical side of it, so the amount of energy generated in terms of electricity, in terms of heat, the parasitic load, so the digester itself will use a certain amount of its own electricity to run. It'll use quite a quantity of its own heat, and then you're looking at the on-site use and the overall value of what you're going to have excess coming out of that. So it's giving you an overall figure at the end in terms of how much value is going to come out of your gas. So in this case, it's coming out with 48,000 euros worth of electricity and 6,000 euros worth of heat. So it's the breakdown of the model. The final page is an estimate based on figures we've seen on the tender process in terms of the overall capital cost of a project. So what we put in there is the digester capacity being one, but effectively the capital cost of the plant, of planning permission, of other infrastructure around that, the energy use equipment, which is your CHP unit, and coming out with an overall total for the cost of the digester. Take away your potential grant, and it gives you your final figures then. You're adding in there your inputs, so your sale of energy being at 53,000 in this example, and ultimately what we're working out is two figures at the end. One is the operating balance during the loan period. So in that case, on that plant, you'll be paying off your loan and you would have 15,000 excess at the end of each year, profit you could say from that project. When you get to the point of having the loan paid off, that would rise then to 40,000 euros per year. And it's giving you a payback period then in terms of years return on investment. So in terms of, that model, it will be available online, and it's a good starting point to assess a project. Look, ultimately, if you go and get caught when you're going down the road of a plant itself, you need to get a tender process going, and it'll give you your determined cost. But this is the best we could get from the tenders we've seen, and we think it's quite accurate. We put in calculation tools there, so that as the digester increases in size, there will be an incremental increase in cost as well. So it's as accurate as we can make it, let's put it this way, for a model. In terms of the value of biogas, and this is just an important concept to consider in any project, we are using CHP now. I'm going to try and break this down a little bit because there's quite a lot of figures on this page. But we looked at 4 potential uses. It's either CHP use, which is the generally one we're seeing. If you're going for vehicle fuel, or agricultural diesel or heat replacing kerosene. And the idea of this was to look at, you're producing a cubic metre of gas, of biogas, what's the actual value of that? How do you determine your overall value? So what we've just determined is in the CHP unit, if you're just producing electricity and you've no value for the heat, you're not able to sell the heat, it's coming out about 64 cents per metre cubed. If you manage to sell all of the heat, it'll be another 24 cents, so ultimately 88 cents per cubic metre of biogas that you produce. If you go to vehicle fuel, it's coming out at just about 70 cents. Now that's comparable, quite okay along with the CHP unit. We have included conversion costs in there as well at 5 cents, so there is a number of things in there. Agricultural diesel, if we're replacing that, and again this is technologically in progress at the moment. We see New Holland selling biomethane tractors, and it's something that they see very much as the future powertrain for tractors rather than any other technology. They see biomethane, they don't see hydrogen, they don't see electric. That's where their focus is on. So it is something that in the future we should see more of. And the last one then is replacing kerosene. And that was actually surprisingly quite valuable, and you'll see in some of the farms we look at later on that replacing kerosene is quite a viable option because it's got a relatively high cost and it's something that you see a lot of on the farms. So in terms of the 3 farms we looked at, in detail we had 8 detailed models done, but there was 3 we were progressing towards the planning stage. So the first was the Hayes Tipperary cheese. So they're an on-farm cottage cheese producer. They take on all their own milk, produce cheese on site for sale into various markets. So we modelled this on 400 cows. That would give us feedstock of about 10 tonnes a day from the yard. There was also going to be 16 tonnes a day, an extra 6 tonnes approximately of whey. So producing cheese, you're getting a lot of whey coming off. Whey is quite a useful substrate. It'll produce a little bit more gas than your slurry. So in total we would have about 6,000 tonnes for a year for that plant, and the biogas output will be about 600 metre cubes per day. So in terms of, sorry, that should be just electricity rather than electricity and heat displaced. In that project we were looking at just the heat because the production of cheese is quite energy intensive. That farm was using quite a lot of heat on a daily basis, and so the displacement of kerosene was actually the most valuable use we came across on site. So in terms of that plant, based on the current kerosene use, it was going to be saving approximately 100,000 euro, 107,000 euros a year, which was 82% of the heat requirement. So to give you an idea of the heat requirement on site when you're producing that amount of cheese, it's a big cost. So that actually was a very viable option financially. So we were very interested in that project. Again, we have a lot of cheese producers, cottage cheese producers around the country, and so it would be one that we could model out on more farms. So again, digestate would be amount produced would be slightly less than 6,000 tonnes, and that gives you lots of benefits in terms of your nutrients being recycled back onto the farm. So the Gavigan plant, which was the second one in Cork, it was again another cheese farm, 250 cows, plus they also do a line in various pig meat products. So they would have 600 finishing pigs on site. Again, this is a plant, 6.2 tonnes per day on the farm materials, 7.6 when you added in the whey, some whey silage. So little under 3,000 tonnes per year of feedstock. With this one went to tender. I suppose just as Sean was saying earlier, the Hayes one didn't go to tender because we had issues with planning. A lot of the issues we came across, examples where the council, some were looking for, because they've seen whey going in, they were saying, well, is this now a waste plant? And they wanted to look at waste permitting. So there was little inconsistency, even though this is material that's going out on farm anyway. There's a lot of, those sort of issues came up that we were not expecting and did cause difficulties for various sites. So in terms of the Gavigan plant, that did go to tender. We got various quotes from that. Hope that's not too commercially sensitive, but about 390, it was not for this project because it's government funded, up to 450,000 for costs. So in terms of a capital grant, it would go up to the max of about 200,000. The cost to the farmer there, as you can see, from about 200 to 240,000. So in terms of the biogas output, a little under 200 cubic metres per day. It was going to displace quite a bit of electricity, a little over 400 kilowatt hours per day. it was going to also displace a lot of heat requirement for the cheese production. So you can see there the overall figure coming down at the value to the farm, or the savings to the farm, will be about €50,000 a year after meeting its own energy demands. So it was going to have a payback of about 9 years, and obviously recycling the nutrients as well. So it was an interesting project. Just in terms of the farm themselves, we got to that stage and decided they didn't want to proceed with it at this point in time, but it is something that in the future they're very much like the project, but they weren't in a position to proceed at this point in time. Riverview Farm, which we'll hear a lot more of today, which is progressing and under near completion on the construction. So a little bit different from the other farms. This is an organic farm. So 200 dairy cows, 3 robotic milkers, and one of the advantages in this site was the fact that it's a lengthy winter, 6-month winter, and the cows will be in at night a lot during the summer as well. So there's a year-round level of slurry production. On this plant, about 4,000 tonnes of feedstock per year we're estimating. The capital cost is coming in around 450,000. And that includes we're modifying an existing slurry store to turn that into a digested store, so adding a cover onto that at 35,000. The capital grant at 50% will be coming about 226,000, so the cost to the farmers is similar to that. The biogas output nearing 500 cubic metres per day, and the big factor in this is the displacement of electricity, and the displacement of a certain proportion of the heat. The robotic milkers do their own hot washing, and they require a certain amount of kerosene to complete that, so we will be displacing all that kerosene. So in around €32,000 a year in terms of total savings, and the payback in a little over 7 years. So that has been produced under construction at the moment by Tank Storage Systems, which you'll hear from later on today. We did receive a number of tenders from that. Another one, there was 4 responded to the tender. Another one we'll hear from later on today, which is bioelectric. And again, the standard of tenders we received were all very good. We would have been happy with any that came forward, particularly the final 2, which you're hearing from today. And look, the technology is there. That's one thing we were fearful at the start of this project. Was there people that would build plants of this scale? And there is ample amount of that in place. So a quick overview of Riverview Farm Biogas. So if you can see there, the mouse is not actually showing there. So the large square box to the closest to me here is the cow shed. So inside there you have the cubicle house, you have the robotic milkers down towards the middle of the screen, and the dairy systems are all up the top here under the grey part. The larger circular on the screen is the existing overground slurry store, which has been converted for digestate. The smaller one over to the left is the digester. The square box in the middle is we have 2 units there. One is the CHP unit, which is slightly behind that, and that is going to be the store for your digestate, your solids digestate, and also for some farm manure that's going to be used for feeding it. You can just about see above that smaller circle there's an even smaller one. That's the input tank. So all of the solid materials, farm manure, waste silage will go in there for mixing before going to the digester. And you can see the 2 red lines, like a triangle coming out of the sheds. That's the line bringing slurry, which has been constructed. It's going to a manhole reception point and then been pumped over to the main biogas plant. So that's just an overground in terms of coming off an aerial image of it. Again, your CHP unit and the stores in place. So the plant is under construction. This is some time ago, so you can see there the cover tank is the digestate store, was the existing tank. The nearest tank in the foreground is the digester. At this point, the cover hadn't been put on it because you want to avoid putting a cover on until you're ready to run. And then the smaller tank just before you there is the input feed tank. So that's another view of the input feed tank. So again, that's just basically a mixing vessel where you put in your farm manure, put in your slurry, mix them into a continuous slurry, and then pump it into your digester. Just some pictures of the tank itself. So again, standard enough. You have heating coils going around the inside of the tank. It's nothing too basic. The only thing different about this and another tank is it's insulated, it's covered, it's agitated. You can see the agitator there. There's 2 agitators in this plant, in green on the bottom, and then the blue line then is basically input coming in with slurry. So a couple of modifications. They're not that different to a standard tank. The top ring would be protected from gas. The biogas in its raw form tends to be highly corrosive, so that's been treated with an additional protection to prevent it being corroded by the gas itself. You'll see older tanks that were built 20 years ago where there's no protection, concrete tanks, and it literally have eaten back 3 inches of concrete, gone away, eroded with the acidification. So it's important for the raw biogas to protect everything from that. So the main challenges we did come across within the project would be probably centred around 2 areas. One was planning, which Sean had gone into quite a bit earlier on. So we did find that there was a lack of understanding of the farm scale biogas plant. So as soon as you went to a planning authority proposing a biogas plant, their initial thought was a large industrial plant, trucks coming in the road, more trucks leaving with digestate, and it was going to be, they just pictured large projects, which exist, and we will see more of them built. But they seen this as something much greater than the actual farm operation. So it took a bit of time and a lot of explanation to explain, and they mightn't even see it in the first explanation, that this is not going to be something you're going to see loads of feedstock coming in and loads of materials going out, as opposed to the normal. So that took a bit of time. We did find then as well that in one case in particular, the planners viewed this biogas plant, well then it's going to be a waste permittable facility. You're now dealing with a waste material. This is taken slurry which has currently been spread on land, but the fact that you're going to put it into a digester first, we're going to consider it a waste facility. So that would obviously sets off alarm bells for everybody. So that caused some considerable difficulty in one project in particular. So we did find, look, each council had different approaches. There's no standardised approach for them, and there does need to be some guidance for the planners so that they can understand exactly what's proposed, and so that there's a standardised process across the country. Again, there was some variability in the environmental requirements. I said that about the waste permitting. We did find, obviously, there was ecology reports, detailed reports required for each farm. You might question why that's required, but that did take a particular amount of time, both in finding ecologists and then being able to schedule in the work. So the other main challenge, so that there were planning permission issues that did hold up all projects for some time. The other thing was electrical connection challenges. So even the form of what type of application you're putting in, there's FP7s and FP9s and all different forms and types of connections you can have with the ESB. Nobody seemed to really know what we wanted or what they needed us to do. We actually had applications went in for one form, which then had to be withdrawn, to put in a second form, they had to be withdrawn, and we go back into the original. So what we did find within the ESB networks, the staff they were very interested. They were very willing to help. They found they were very interested in this whole area, but there was no internal process in how to handle this. There was no procedures for how they could do this. So that caused considerable confusion and time delay, and getting the right people to talk to was even a difficulty in those scenarios. When we did find them the individuals are very good to us now, I have to say. But even at that, it was just very difficult to get stuff through. And that did cause one project, was really a main part of why it didn't proceed. So I suppose the general learnings we found in this project would be huge level of interest across all farm sectors. We've seen that with our information meetings. There is a lack of information in terms of the different scales and levels for biogas. It has been we need more technical knowledge out there. There was significant confusion over those different scales from both authorities and farms, and there does need to be clear information on that. So we did find that, look, within that, the concept of having an on-farm plant that's just for that individual farm was very popular though. The main practical learnings we came from this project was that, look, you need to have all year-round supply of feedstock was critical. Beef, we went through the beef and dairy earlier on, but nothing, I won't go through that again. The farmers tended to underestimate the amount of feedstock required to run a plant, and there was a need to really look at the biogas yields coming off each plant. So the other times there really, in terms of the scraper systems I talked about earlier on, in terms of having fresh slurry coming in for each plant. In terms of the main findings of this, in terms of research, policy going forward, what we think could be needed in the regulation side of it, First off, better understanding of the on-scale, farm scale and large-scale plant. Does need to be clear distinction on those. There is under Type 9 ABP regulations, which has been very helpful. But there is a lot more research required in terms of looking at the full soil, the fertiliser value, soil enhancement, and the nutrient availability of digestate and the carbon implications of same. So there's a lot of, we are finding those numbers we would like to have coming out at the end of the project. Some are limited because of the fact that there is more research needed in this area. Look, it's developing a biogas industry here in Ireland is going to be a multi-year task, and there's a lot of learnings to happen over that period of time. So there's other information here which we're going to have on the slides going out to you all, so that you can read through these. But again, much of this I've said already in terms of there is a need for capital support, there's a need for technical support, there's a lot of potential for this on farms. The on-site, on farms, mostly CHP seems to be a viable one, but if there is a need for a heat source nearby, with one farm we did look at, which was very interesting early on, was one where they had a nursing home next door, and just 200 yards away, and supplying heat to that was a very viable option. So there is many things we can look at here, and that would have been supported under the SSRH. So no, there was no two, like any farmyard, there's no two farmyards the same, and there's no two plans in these the same. So in terms of the overall reduction potential, in terms of stored slurry emissions, they tend to be reduced by about 11% in terms of erroneous emissions coming off slurry and storage. When you go to, so that reducing that is critical. The fossil fuel heat displacement was important. Replacing electricity was critically important, but the nitrogen availability in the digestate was also a critical factor in this. We are assessing these at the moment. We will have them completed shortly, but the numbers on these are starting to look very interesting in terms of carbon savings and overall impact. So that's really, I won't go through those too much more, but I suppose in terms of the policies identified, the microgeneration support scheme, we would look that should include biogas. What we're finding is these support schemes tend to be geared towards your intermittent technologies, it's like wind and solar, and at the moment, anything going onto the grid, they're always looking for kilowatt hours, but regardless of when they're produced. What they're not taking account of is the fact that something like a biogas plant produces power 24/7, all year round, and it supports the grid, it gives grid stability, and that needs to be valued. And that's a discussion going on at ESB level, where there needs to be more and more value put on for what we need. We need a stable grid as well as low cost electricity, and providing that stability is important. The small scale renewable electricity scheme, again, leads into that. The actions around planning permission, definitely in terms of stakeholder awareness, planning authority awareness is important. The agricultural emissions, and there's a big distinction between agricultural emissions and energy emissions. If you produce biogas on a farm to produce electricity, you are lowering the emissions of that farm by displacing a fossil fuel. However, the benefit of that is not attributed to agriculture, it's attributed to the Department of Energy. So there needs to be, because it's gone into an energy field. So if you put all that savings you've made doesn't go to agriculture, and there needs to be a rebalance of that, so that if you can account for it in agriculture can value it, and it helps to pay for the overall project. So that needs to be put forward. In terms of the agricultural emissions, obviously erroneous emissions of methane, reducing the need for chemical fertilisers, all of that really adds into the viability of it and the overall positive environmental impact. So those are numbers we're coming forward with in time. We have some base numbers, but we're not going to publish them at the moment, but that's sort of effectively where it's coming from. Thank you.
Thanks very much, Noel, for your presentation. I know both my own and Noel's presentations probably triggered questions for you, but please just hold them for a few minutes and we will take them.